I'm going to talk about CO2 location by deep learning inversion of gravity data. My name is Xianjin Yang from Lawrence Livermore National Lab. My co-authors are Xiao Chen and Megan Smith. CO2 leakage in shallow aquifers increases CO2 saturation and decreases the bulk density of the formation. Surface-based gravity monitoring method can detect these density changes. Conventional gravity inversion method has a poor resolution in estimating the depth, size, and the density of a target. This is a typical gravity inversion result. The density image is very smooth. Two white rectangles show the target boundaries. We can see large errors in predicted target depth and size. In fact, the estimated density also has a very large error. We developed a deep learning inversion method for higher resolution detection of CO2 leakage plumes. To train the deep neural networks, we created over 200,000 artificial synthetic CO2 leakage scenarios. We sampled 3 CO2 plume parameters, 6 depth levels from 0 to 1,000 meters, 12 saturations from 1% to 50%, and then 10 plume volumes. The corresponding gravity monitoring data are generated by gravity-forward models. We randomly chose 32,000 samples from over 200,000 scenarios because of inadequate computer memories. Most of scenarios have 2 CO2 plumes. We used UNet for deep learning inversion of gravity data. The input is a surface-based gravity monitoring image. The UNet output is a 2D cross-section image of CO2 distribution. UNet is a U-shaped convolutional neural network, initially developed for medical image segmentation. Image segmentation is often used to locate objects on an input image. Deep learning inversion is much more complicated than a simple image segmentation. We need to locate subsurface CO2 plumes from surface gravity data. These are 2 completely different images in 2 different spatial domains. We compare the predicted CO2 plume image by UNet with the true plume model. These are 8 pairs of true model versus predicted CO2 plumes. The deep learning method can locate CO2 plumes among 85% of leakage scenarios with noise-free data. The most impressive results are detection of small and low saturation plume, and also deep plume. Our deep learning inversion method shows a significant improvement over the conventional gravity inversion, and it can detect small, deep, or low saturation CO2 plumes. Our method provides quantitative information for risk assessment of CO2 leakage. We optimized hyperparameters for better resolution of CO2 plume location. Noisy data results in artifacts on the predicted CO2 plume image and lowers detection fraction. Our next step is to train the UNet with physics-based simulation data. Thank you.